Welcome to the exercises for chapter 18. This is mostly a chapter on kind of high-level discussions about how biases get introduced into science and statistics. So there aren't that many exercises, but I think it's nice to have a few just to demonstrate how you can apply basically just small things to your data, small transformations of the data to change the statistical significance of the results or introduce biases into the result. Okay, so this first exercise, we're going to go back to a concept called data trimming. This is something I introduced in the chapter on data quality control and cleaning. Data trimming basically means that you remove either a certain number of data points that are extreme, or you remove a certain percentage of data points. Okay, so there's two parts to this exercise. I'm going to explain the first part and then switch to code. Then I'll come back to explain how we transform that first part into a experiment. Okay, so to start with, create one data set comprising 30 numbers randomly drawn from a standard normal distribution, just a regular Gaussian distribution. Run a t-test against the null hypothesis that mu equals 0. So the population mean is 0. Now, these data were drawn from a population with a mean of 0. So, in fact, we know that the null hypothesis is true because we are simulating data where the null hypothesis is true. So we certainly expect the t-test to be non-significant. Okay, so then what you want to do is remove or trim the two most negative data values. So from the distribution of these 30 data values, the two numbers to the left of the distribution, just get rid of them, completely remove them from the data, and recompute the t statistic. So you might get results that are something like this. Here you see it's non-significant in both cases. The degrees of freedom are 27 because we now have 28 data points. You can see the t-value got larger. It's still non-significant, but the p-value is basically halved, more than halved. So it is closer to statistical significance. Now, once you get this code running, just run it a bunch of times, you will see various outcomes. You will actually find cases where this is non-significant and this is significant. You'll get negative t-values, all sorts of diverse outcomes. So let me switch to code. I will show you how I implemented this part of the exercise, and then we'll come back for the experiment. Here I specify the sample size. Here I generate the data. Super simple, nothing terribly interesting. Here I'm removing the two data points to the left. And the way that I do that is by sorting the data. Now, I'm not actually sorting the data itself, although you could do that as well, and then just remove the first two data points. But I'm not actually resorting or changing the data set. Instead, I'm coming up with a set of indices that tell me which data values are in which order. And then from that index, I say data trim. So I'm making a new variable that equals the original data set, but only the rightmost 28 values. So I'm ignoring the first two values, indices 0 and 1. And these are, again, not the first two indices in the data, but the first two indices in this variable IDX, which is the indices of the data sorted according to magnitude and sign. Okay, so then very simple, I do a t-test on both of these data sets. The O is for original, T is for trimmed, and then I report the results here. Okay, so here you see an interesting case where the original t-value was negative, but then we removed two negative data values without changing any of the positive values. So the t-value became positive, highly non-significant, not even approaching significance in either of these cases. Okay, here's where it approaches statistical significance, but does not reach it. I'd like to find a case where it goes from being non-significant to statistically significant. Okay, here is an example. So this is still non-significant. The p-value is, we could call this marginally significant if you cared about this. But this is highly statistically significant, 0.008. So we went from non-significant to strongly significant with a very small p-value, well below our p-value threshold, by removing two data points. So now for the experiment. Essentially, you're going to take the code that you just wrote and repeat it 1,000 times, each time generating a new data set. So we're basically going to count the number of times that we got a p-value less than 0.05 with the random data and with the random data that were trimmed. Okay, but now there's going to be two different kinds of trimming. There's going to be what I call here asymmetric trim, and that is exactly what you just did. So you remove two data points from the left side of the distribution, the two most negative values of the data set. So that's what we've already done. And then we have a symmetric trim. And here you are removing the most extreme value from the left and the one most extreme value from the right. So all of this means that you start off at each one of these iterations. You start off by creating 30 numbers drawn from a standard Gaussian distribution, and then you make two copies of that data set. One copy, you trim the two values to the left, and one copy, you trim the two values, the two most extreme values, one for the left and one for the right. So in all of these cases, the data sets will have 28 values that are, so the trim data sets will have 28 values that are the same as the original n equals 30 data sets. Okay, so then you can compute the number of times and also the percentage of times that you got a p less than 0.05 result. So this is the original data without trimming, the symmetric trimming, and asymmetric trimming. I'm going to have a few things to comment about these results when I switch to Python. And then there's one more thing we can do with this exercise. There's many things you can do with this exercise, but there's one more thing that you should do with the instructions here. And that is inside this for loop over the 1,000 different random data sets, store not only whether the p-value was less than 0.05, but also store the actual t-value, because we can make a plot of the t-value. So that's going to look something like this. Here on the x-axis, we have the original t-values. So these are the t-values from the full n equals 30 data set. And then on the y-axis, we have the t-values corresponding to the trimmed data set, either the asymmetric trimming or the symmetric trimming. Now, here I'm also plotting the unity line. So if the trimming did absolutely nothing whatsoever, if we didn't change the data at all, then every single point would lie on this line of unity. So the fact that these lines or the dots are off the line of unity tells us that something happened to the t-values, that it is systematic. So we introduced a systematic bias to the result of the t-test by trimming, and I'm going to explain what that bias is and what it means when I show you this plot in Python. So here we are with the experiment. You can see, you'll recognize most of this code as being the same as in the previous cell. I have some new values here, which are, because we need to store all of the outcomes from all the experiments. And then the 3 here is because we need to store the results from the original analysis with the original data set, the trimmed on the left, the asymmetric trim, and the symmetric trim. Okay, so here's the data, just like before. Here is how I trim. Here I call it left instead of asymmetric, but this is the asymmetric version. And then here I call this B for both, but this is the symmetric trim data set. So you can see the code looks really similar. Here I'm just taking, I'm excluding the first two values. Here I'm excluding the first and the final value. Okay, so then we do 3 t-tests. Again, the code is basically exactly the same. We're just using these different variables, which all come from this data set. Here I'm storing the significances, whether the p-values were less than 0.05, and the actual t-value. So here are the results, and what do these results mean? So first of all, we can look at the proportion or the percentage of times that we got a significant result, so p less than 0.05, without any data trimming. Now, as I mentioned in the beginning of this video, we know that the null hypothesis is true. So in fact, we should find that p is less than 0.05 0% of the time. But, there's random variance and sampling variability and so on. And so with a p-value of 0.05, we expect that around 5% of these samples will be incorrectly labeled as statistically significant. These are alpha errors, they are type 1 errors, And 5.9 is above 5%, but we do expect there to be around 5% of cases where this happened. Okay, and then with symmetric trimming, we see it's basically doubled, and with asymmetric trimming, it's basically tripled. Now, the fact that it's doubled and tripled is not meaningful, but the fact that it increased here with trimming is meaningful, and the fact that it increased here with asymmetric trimming is meaningful. This is a systematic bias that we are introducing to the data. So, in fact, here we are. Well, actually, now I will talk about what the nature of that bias is, because it turns out that there are separate biases introduced here versus here, and they have different implications. So I'm going to talk about that now. Here is the code where I create the plot that I showed. Pretty straightforward. I'm just plotting the t-values from the original data set by the t-values from the asymmetric and symmetric data sets. Okay, so here is what that figure looks like. So let's first discuss the asymmetric trim. What you see is that all of the white circles or light gray circles are above the line of unity. What does that mean? That means that the t-value after trimming is always higher than the t-value from the original data set before trimming. And it's not more extreme. So even when it's negative, it's always going to be more positive, regardless of the sign. So there is a systematic bias that we have introduced by pushing the t-values up. We are more likely to get a statistically significant result, even though we know that we should not be getting any statistically significant results. We should be getting, or we expect, around 5% of the time we get a p-value less than 0.05. But in fact, we are seeing much higher. It's around 14% or 15% of the time we get a significant effect, even though we know that the null hypothesis is true. So that is a systematic bias that we have introduced. Okay, so how about these dark gray squares? This is for the symmetric trim. Now, what you see here is the squares are below the line of unity here for the negative values and above the line of unity for the positive values. So basically what that means is that the t-values are getting stretched out. They are getting further away from zero. So the result is just more likely to be statistically significant regardless of the sign. So more likely if the original t-value is negative, the trimmed t-value is more negative. Now, why does that happen? Well, basically what we're doing is decreasing the standard deviation. And remember that one of the assumptions of a t-test is that the data are Gaussian distributed. And what we're doing here is actually clipping off the tails a little bit. So we are making the distribution be slightly less Gaussian. We're making them slightly less or have slightly less kurtosis by removing the tails of the distribution, or at least, 1 point from each tail of the distribution. So effectively that shrinks the standard deviation. And of course, the standard deviation is in the denominator of the t-statistic, which increases the overall t-value. So I hope that makes sense. In both of these cases, we are trimming the data, and that actually introduces some biases to the statistical analysis, but the nature of the bias depends on exactly how we applied the trimming. Welcome to exercise 2 in chapter 18. In this exercise, we are going to go on a fishing expedition. That's what it's sometimes called in data science, when you're just randomly mining a data set and just looking for significant results without having any hypotheses to guide your analyses. Okay, so what you want to do is create a data set that contains 10 variables or 10 features and 50 samples or 50 observations. And I'd like you to work with pandas in this exercise just to give you more experience working with pandas and also with Seaborn. Okay, so from this data set of 10 features and 50 observations, compute all pairwise correlations. So correlate every possible pair of variables, every pair of features. And then what you want to do is just pick out the one that has the largest magnitude correlation, whichever one it is. These are variables that are completely random numbers. So we have no reason to suspect that any one particular feature will correlate with any one other feature. It's literally random numbers. And we just want to search through all of the 45 correlations that we get and just pick the one with the largest magnitude correlation. Then you can compute the p-value and make a scatter plot that looks like this. So in this case, it happened to be that variable 4 and variable 9 correlated at almost 0.5 with a p-value that was less than 0.001. This is a pretty respectable correlation coefficient. It's a linear relationship that would make many researchers jealous. This is a pretty strong relationship for many areas of science, especially areas of science that involve a lot of individual variability, unaccounted for variability like psychology, sociology, medicine, biology, all sorts of interesting areas in science would have correlations of 0.5. And you can write a paper, you can get a result published based on 0.5. And here we literally found it in random numbers just by correlating everything with everything and seeing what happens to come out. Okay, so that's the most important part of this exercise, just to see how easy and often this happens. If you like to do some additional work, you can also compute and plot the correlation matrix along with the significances, Bonferroni correcting for the number of comparisons. Now, in this particular case, this correlation actually survives multiple comparisons correction using Bonferroni, which, as you know, is a conservative method for correcting for multiple comparison. So the point is, even correcting for multiple comparisons does not guarantee that you cannot get a spurious correlation, a fake correlation in data where there is no real population relationship. So here is the code to create the data frame. You can see I'm generating random numbers. So this is a matrix of random numbers, and I'm specifying the columns to be V and then the column label. So these are completely arbitrary. You don't even need to include the column labels if you don't want to. Okay, so that's our data frame. We can get the Pearson correlation coefficient matrix by using the method.core. Now, this method returns the correlation coefficients. It does not compute and return the p-values. So we're going to need another way to get the p-values from this matrix. I will show that later. Okay, so then I'm using this function called numpy.fillDiagonal. I don't know if I've used that elsewhere in this book, but basically we want to ignore the unity correlations. So I'm setting all of the diagonal elements to be 0. And the reason why I do that here is because I'm going to identify the largest number in this matrix. Now, obviously, the largest number in a correlation matrix is always 1, always a diagonal. So by setting the diagonal to be 0, basically that just facilitates the rest of this algorithm. Okay, so here I'm using numpy.where to find where the correlation matrix is equal to its maximum. So this returns the largest absolute value in the correlation matrix, and then this whole thing returns the indices. So this is the row and the column index where we have the maximum correlation. Okay, so then to get the p-value, I'm using scipy.stats.pearsonr for only those columns. So now I'm just correlating one specific pair, but it's the pair that I already know has the largest correlation coefficient. And this one is because the first output is the correlation coefficient, but we already know that. We just want the p-value from that correlation coefficient. So this is the way that I set up this algorithm. There's several other ways you could have solved it. So if you solved it in a different way, you computed all pairwise correlations, let's say in a double for loop, to also get the p-value at the same time. That's great. However you solved it, as long as you solved it, that's the important thing. Okay, so then we make a scatter plot. I'm using Seaborn. It often is the right way to visualize results from a pandas data frame. And here I'm just specifying that X and Y come from these two columns in the data frame that showed the strongest correlation. So I'm super curious what the result is in this particular case. Oh, here we got a negative correlation. So it turns out that in this data set of purely random numbers, 10 random variables, we got a correlation of minus 0.42, which has a p-value of 0.002. Again, if you saw this in your data, you would probably be pretty excited and start telling your supervisor and your friends and colleagues that you have this amazing result. But here we see that it just comes from pure noise. Okay, now I don't know if this is statistically significant given Bonferroni correction. That's something we can do here. Okay, so this code is copied from exercise 1211 from several chapters ago. I made a few minor adjustments, but nothing really significant. Nothing important is different. Okay, and that shows this correlation matrix, which you might remember from previously. Okay, so let's see. So it looks like I don't see any asterisks here, which means that in fact, this correlation that I showed is it would be considered statistically significant without correction for multiple comparisons, but when we correct for multiple comparisons, it disappears. So in this case, I would consider this to be a success of Bonferroni correction. We didn't have any hypotheses. All of the pairwise tests all the pairwise correlations were independent of each other. So that conforms to the assumptions of Bonferroni. And it completely eliminated all of the correlation coefficients. I'm going to run this again to see if we get a stronger correlation that might still survive Bonferroni correction. Okay, so here I'm running it again. It's going to have to be larger than 0.42. Okay, so I ran this code a bunch of times, literally just creating new random data over and over again. Here I got a correlation of 0.45. Now let's see if this one is significant with Bonferroni correction. And it is. Okay, so here again, just generated a bunch of random numbers, correlated all of them, and picked out from this entire correlation matrix. We just picked out the one correlation that was the largest magnitude, and it turns out to be statistically significant when correcting for multiple comparisons using the Bonferroni correction. So this exercise is an illustration of a fishing expedition, sometimes called data dredging. And basically the idea is if you have enough variables or you perform enough tests, it's likely just by chance that something somewhere will be significant. This highlights the importance of having really strict hypotheses, or at least some weak hypotheses that help guide you to know which are the proper analyses that you should be running.